Hello and welcome to EELE 367 Logic Design. My name is Brock LaMeres and I will be your instructor for this spring 2021 semester. In this video, which is the introduction to the course video, what I want to do is get you ready to engage in the course. So I want to talk about what is this course about, who's the instructor, who am I, if you don't know who I am, just a quick background so you know who the voice is in all the videos, and what we're going to be doing. So I want to go over the syllabus, and specifically I want to talk about the format we're going to be using this spring, which is COVID blended, and where will we be doing it. And I want to walk you through Brightspace and show you where everything is and all the links you're going to click and get rocking. Okay, so let's start with what is this course. It starts to help with the Prereq. This is a continuation of EELE 261, which is Introduction to Logic Circuits. So this was the whole truth table, Carnot maps, state machine thing that you should have taken. If you didn't take 261 at Montana State, you should have taken one at a different school, but you need to know the following material. If you recall, 261 started with just a brief description of the differences between analog and digital signals and systems. And then we talked about number systems. So this is where you learn to count in binary and add in binary. And we talked about things like two's complement representation and things like that. And then we looked at digital circuitry. So this is where we actually breadboarded up AND gates and OR gates, and we built and we just talked about power supplies and grounds and just basic breadboarding skills. And then module 4 was the big one where we started talking about combinational logic. And this was things like, from a truth table, can you synthesize a canonical sum of products form and build a circuit? Or can you use a K-map and create a minimized form and build that circuit? And then we moved into an introduction into VHDL. So VHDL is a hardware description language, and it allows us to describe digital circuits using a language and then allowing a tool to actually synthesize the actual gate level circuitry for us. And we did some labs with FPGAs, but again, we just touched on why VHDL was important, and we did some very rudimentary things. And so we looked at the power of a hardware description language, but we didn't really get into it. Then we looked at MSI logic, which was an example of building combinational logic circuits that were too big to do by hand. So we had to start designing them with a hardware description language. And then finally, we buttoned up 261 with sequential logic, which was things like flip-flops and finite state machines. And at the end of that, you built these massive digital circuits on a breadboard, and you said, I want to stop. I don't want to do this anymore. So what is logic design? Logic design is where we say the circuits are too big. We got to start using a hardware description language for everything. And so that is what we're going to do in this class. We're going to look at the advanced modeling capability of VHDL. We're going to only build circuits on an FPGA, and we're going to program the coolest things you've ever seen. And we're going to end this class with a full-blown computer. So we start in module 8, which is actually chapter 8 in the same book that we used in 261. So if you have that book, use it. Don't throw it away. So we're going to start with VHDL, and we're going to learn some more capability within it, and then we're going to start doing behavioral modeling. So we'll start modeling state machines the right way, and we'll start modeling registers and basically sequential circuitry and combinational logic circuitry using more advanced programming techniques. So things like if-else statements and case statements and processes. Then we'll build memory systems, RAM and ROM. We'll look at programmable logic. We'll actually look at the FPGA in more detail and see where the circuitry is going. Then we'll look at arithmetic circuits, so actually building adders and subtractors. And finally, we culminate with a full-blown computer design. We're going to build an 8-bit computer. You're going to describe the entire thing from scratch in VHDL. You're going to program it in ones and zeros, and this will change your life, and you'll just be awesome after this. Okay, so what's the next step? Let's talk about who I am. You're sitting here going, man, this guy's really jacked up about this topic. Who am I? Well, if you don't know me, you might probably had a class with me, but my name is Brock LaMeres. I'm a professor in electrical and computer engineering. My background is I got my bachelor's degree from Montana State back in the 90s. I went to work for Hewlett-Packard where I designed digital test equipment, and my job was to build FPGA designs, I did FPGA design and printed circuit board design and essentially digital system design, and FPGAs were a huge part of what I did. I worked at Hewlett Packard for 8 years in Colorado. And then, like all big companies do, they paid for me to get my master's and take classes on the side. So I did my master's and PhD at the University of Colorado, and ended up saying, it'd be cool if I could be a professor. So a job opened up at Montana State, and I moved up here, and I've been here ever since. So I've been here for 15 years. And my area of interest for research, I'm on my website right here, is actually looking at how you can use these programmable devices to create optimized computer systems. And so the field programmable gate array that we're going to use in this class, and what we touched on in 261, is kind of the basis for my research, because anything you can come up with, you can implement and test it right away. And so what I ended up doing was I was looking at different ways to make optimized computers, and I stumbled across this thing about a decade ago where I realized that when you program the FPGA, you can flush out faults that have occurred in the memory and in the circuitry. So faults like a 1 becomes a 0 and a 0 becomes a 1. Well, it turns out that this is a problem for NASA, because when you put computers in space, the ionizing radiation hits their computers and causes crashes because these bits are flipping. And so we came up with this idea of using these redundant cores on an FPGA, and then not programming like writing C, but actually configuring the hardware on the FPGA locally within one little region while the rest of the FPGA runs, in order to flush out the faults. And that launched this huge design of a computer system for NASA that has resulted in some pretty cool experiments. So we've done, let's see, I have some pictures over here. We've done sounding rocket flights where we shot it up into space. We've gone on the International Space Station. We've built small satellites that are in orbit. We actually have 2 small satellites in orbit right now. This is about the size of a loaf of bread. Here's it getting shot off the International Space Station. And then we've done huge balloon flights, and we actually got selected to go to the moon. So we're going to demonstrate this MSU computer on the surface of the moon probably in 2023. And so that's kind of my background. I also, if I go back to my main, I also wrote the textbook for this class, and also for 261. And this textbook and the whole 261, 367 combo is really the culmination of modernizing the digital logic curriculum at MSU, which I was asked to do after I came back here from working in industry. And so what I did is I kind of revamped these courses over the years, and I've modernized them, and then we developed the curriculum so that could be offered online and live and blended. And then I ended up writing the book, and we're on the second revision of the book. And so that's kind of my background. Now, I tell you this because, this stuff is awesome. This is what I live for, right? I chose this as my area of study in college. I worked in industry doing this stuff. I wrote books on all this stuff. I do research on this stuff. This is what I do. So I love this stuff. This is what I'm really passionate about. So hopefully you'll have as much fun as I am going to have this semester. Okay, so that's me. What are we going to be doing? Let's go over the syllabus. All right, so standard syllabus stuff, here's the course, you already know that. Here's your learning outcomes, that's what you're going to learn. I am actually physically located in Norm Asbjornsen Hall, so that's a typo, I'll fix that. We are going to have a teaching assistant, Stephanie Smith, who's going to be in the labs for you. And now this is the biggest key to everything. Spring 2021, we're still in the COVID pandemic. So we are going to offer this course in what we call a blended format. Blended means you live and online. So we need to do our courses one more semester in a form where we can spread out. So we need some courses to go online to make room for other courses so that they can split sections and get enrollment in each or attendance in each room less so that everybody can spread out. So this is a course that can be taught online. And so we said lectures for this course, let's put them all online and not tie up a classroom. And so you are not going to have a set time for lectures this semester. You are going to watch a whole pile of YouTube videos that I created for you. All right. And then you're going to do a lab, and you're going to do a lab with a portable lab kit. You are going to check out an FPGA board initially, and you're going to do all your labs on that thing. The great thing about it is that if you have this FPGA board, you can do your labs from anywhere as long as you have a laptop. Now you have to have a computer. Usually it's a laptop, but if you have a desktop at home and you just want to work there, that's fine too. But you need to check out this FPGA board, and from then on out, you can do the labs anywhere. Now we are going to have Stephanie in the lab sections for you as an open help session. So the lab sections that are on Wednesday, you either enrolled in a 2 to 4 section or a 4 to 6 section. Stephanie's going to be in there, and you can go in and get help on labs if you want. You can go in there and work in the lab if you want. You cannot come in and work if you want. You can just drop in when you want. Whatever works for you. All the demos for this class are going to be done the same way, where you're going to do it with a video. So you need to have a camera, well, a smartphone, and you're going to actually upload a video of your demo and also your source code, your VHDL, and that's how we're going to grade everything. We're going to do that whether you're on campus, in the lab, or not. And that way that everybody is turning in the same type of material, so that makes it easy for us because we grade everybody the exact same way. But if something happens and we say, man, we need to shut down campus and go fully online for a month because COVID went nuts, we don't even notice, okay? The format of this class doesn't change whatsoever. But here's the thing to keep in mind. You should come to your lab section the first week of class. So that's on January 13th, because we're going to check you out, your FPGA board, and then you're going to meet me, you know me, and you're going to meet Stephanie, all right? And just know that you have a live person there to even make this class better, if that's possible. Stephanie's going to be on a WebEx section too. So when she shows up for her lab section, she's going to log into WebEx, and I'll show you how to get a hold of her on the WebEx section, so that if you're in the lab, you can go over and say, hey, Stephanie, help me. If you're off campus, you can log into the WebEx session and just wait until she comes around and answers you, and you can get help during those times. But here's the key to it all. Your scheduled lab section time is when you can get help. Outside of that, there's no such thing as office hours. We are going to have 4 hours of dedicated TA time where she is sitting there waiting to help you. So it's not like something you can call her at midnight and go, I need help. This is your time to get help. So get used to using these hours immediately and make it part of your schedule. Okay? All right, life is good. Required materials. You need a computer. Macs do not apply. This software that we run, you got to remember this from 261, Quartus doesn't run on a Mac. Get rid of that Mac if you're going to be an engineer. It only runs on Windows, so you got to have a Windows machine or access to a Windows machine. You need a textbook? You betcha. I wrote it. You can use the first edition if you want. There is a second edition. If you're going to buy it through Amazon. It's always cheaper. I even created a little link right here. If you check this link out, if you click this link, it'll take you to Amazon. If you buy it on Amazon, I get like 5 cents or something. I don't know, but I get some money from that. So use that link. Make me rich. Digital Logic Portable Kit. It's an FPGA board. We're going to check it out to you. We're using the DE10 Lite. If you want to look that up, you can get in the Brightspace shell and check out what it looks like from the lab descriptions. And then a camera, which is basically your phone. Got to have that Prereq in there. Brightspace, we're going to use the same shell that we've been using for a while. Office hours, like I say, I'll post office hours on my website, but there's not going to be many of them because we have dedicated time for you to get help on this class. Grading distribution, we're going to have weekly homework. You're going to be doing VHDL and simulating stuff in Model Sim, okay? You're going to have labs where you write VHDL, synthesize it for an FPGA, and demo. You're going to be doing buttons and LEDs and switches. We're going to have end-of-module quizzes just to make sure that you kind of went through the material in the book. Then you have that big old final project, 200 points, 20% of your grade, building the computer that'll change your life. Grading, straight grading, no pluses, no minuses. You get a 90, you get an A. I don't like minuses because if you get a 91, you lose points. You get an A minus, right? But you get a 99%, you don't get no plus. So no pluses, no minus. Sometimes I give a plus if you're really crazy, but I'm not I hate minuses. Always have. What you will be doing in this class is the following. Reading. There's a book, okay? Instructional videos. If you don't like to read, you can do the videos. They're the same material, okay? I wrote the book first. I recorded the videos up on the same material, whatever mode you like. You will be doing homework, which is going to be mostly in the form of model sim simulations of VHDL. But there are some online quizzes that are automatically graded. The lab, this is where all the magic happens, okay? That's where you learn how to write VHDL and synthesize it and actually build hardware. And then you got these end of module quizzes, and then the final project, big one. Okay, academic policies. You've heard this a million times. The biggest thing is the difference between cheating and collaborating. You have to collaborate to be an engineer. Nobody solves problems alone anymore. Work with your colleagues, work in small groups, whatever. But every single one of you needs to type in your own VHDL. The days of getting together at a computer, at a keyboard, and only one person types and two people stand behind them and say, oh, do this, do that, they're over. You're typing every line of VHDL for this semester. You got to do it. Even if you're in like a group and there's like 10 of you sitting around going, how'd you solve this problem? How'd you solve this problem? Everybody types. Okay, so you got to have your own machine. You got to have your own software, your own FPGA board. You got to do it. Okay. Cheating is where you just say, send me that file and I'll upload it. Then that sucks. You get kicked out of college. Don't do that stuff. Masks, got to wear masks. There's nothing new about that. Socially distance, all that stuff. Wash your hands. Okay. So that's what we're doing. This right here is your buddy. This, you don't want to misplace this. It's online. It's not going to get misplaced. This is the schedule. This is what you are going to be doing every week for this semester. It's going to show you what you're going to do. It's going to show you what's graded, what you're actually going to get graded on, and it's going to tell you when the assignment is due. So week 1, you'll notice we're doing course intro. That's what we're doing right now. There is a review of classical digital design. That's everything from 261. I have an online quiz for you to do that's due the first Wednesday of the first week of class. It's actually worth extra credit just to get you to do it. Then you start getting ready for the VHDL stuff. So then in week 1, we actually do some VHDL. There's a couple of assignments. Every single section that we cover will have a homework assignment, whether it's in the form of a multiple choice quiz in Brightspace or a VHDL assignment. Your first week, you're doing VHDL. Okay, you're in Model Sim. You got to get the software installed. You got to get going. Okay, everything is due the following week on Wednesday at 6 p.m. Okay, that means for the activities during week 1, I want you to work on them during week 1. They're all designed to be accomplished during the week. If you get stuck or something happens, that gives you the weekend, and then you can come back and on Monday get help, Tuesday get help, and Wednesday, more importantly, you can go to your lab section and get help. So that 6 p.m. corresponds to the end of the lab section the following week. But you should really get used to doing the material during the week. If you try to start doing this thing where you like start working on it at 5:30 before the deadline, you're screwed. You're going to fail the class. It's guaranteed, because these assignments, you remember them, they take a long time to code and compile and synthesize. There's no way to do it last minute, so just keep on it. But this schedule is going to, you want to look at this every single day, every single week. You want to make sure you know what you're doing, what's graded, and what you're going to be actually doing. Okay, you've worked through it. It's all color-coded. It's some of my best work. Look at this computer project. It's like 5 weeks. It's the greatest. It's going to change your life. I'm not kidding you. It is so cool, but it's a chunk. It is 20% of your grade, and it is a lot of work. And that's why I'm giving you, it's almost over a month that we're going to work on that. Okay, let's do the final wrap up on this. Brightspace. Everything's in Brightspace. Here you go. You come into Brightspace. You come down here. You see your courses, logic design. You come into here. I show you a picture of the book. Just get you all jacked up. This is just an announcement. I'll put announcements here, and I'll email you when I have stuff to say, and I'll also copy the email here. So that's where you're going to get information. Everything in this course is linked into content. So if you click content, what you're going to see is in here, you'll see the course information and syllabus page. You'll see a module 8 page, module 9 page, 10, 11, 12, and 13. That's it. When you go look at one of these module pages, what you'll see is you always say this corresponds to a chapter. You're going to see the learning outcomes for the chapter directly out of the book. Then you're going to see what you're actually going to do. For each section, it kind of looks like this. You are going to read, watch a video. You can do one or the other or both, whatever you prefer. And then there's a homework. So every section has a homework. Look at section 8.2. You're going to read or watch a video, and a video. Section 8.2 is a little bigger than 8.1. So you had 3 videos that I broke it up. And here's your assignment. Do this homework. Look at the difference between 8.1 and 8.2. You go click on 8.1. It takes you to a quiz. All right, not a big deal. 8.2 takes you to a VHDL assignment that you have to do in ModelSim. And right here, you're going to upload it to the assignment folder, and then we will grade it later. Now you're like, man, it seems like this was 8.1 was a lot easier than 8.2. It is, and that's reflected in the points that you get. So look at the points that you get for 8.1. You get 2 points for that little quiz. You get 12 points for the VHDL simulation in ModelSim. So when you look at this, be aware of the points associated because it reflects the amount of time that's going to take to get through some of this stuff. Okay, and look at it. You just repeat, and then all of a sudden here comes a lab. Okay, you got a lab, it's like you got a description. I even give you an overview video where I show you kind of how to get started and everything. And then you upload your lab video, demo, and your source code to the assignment folder, okay? Then here you go again, section, lab, whatever. All right, now check this out. If I click here, you got module 9. Looks pretty familiar, doesn't it? Each section is read and watch a video, do a homework. Read and watch a video, do a homework. Oh, you got enough information? Do a lab. Okay, repeat. You just crank this thing. Just keep cranking. Memory systems, same exact format. You might be saying, the labs are going to take a long time. Do I get more points for them? Look at how much these labs are worth. 50 points right here, okay? The little quiz on 8.3 is worth 3 points. The homework simulation is worth 14. The quiz is worth 50. The lab is worth 50. The lab is where all the learning takes place. Okay, so that is what you're going to do. All right, so now you're sitting here. You're so excited to get started. The question is, what do you do now? So here's what you got to do. First of all, read over the syllabus. Just try to get familiar with it. Poke around in Brightspace. And then when you start class on January 11th, go ahead and start working through the videos, working through, reading, working through some assignments, install the software. Okay, there's videos in there that show you how to install Quartus and ModelSim, and you're going to have a simulation due the second week. And then show up to your lab on Wednesday the 13th because that's where we're going to check you out your FPGA board. After that, you can work in the lab, like I say, or you can not work in the lab. You can do it remotely, whatever. But you got to get that FPGA board the first week because we're doing a lab the second week of the semester, okay? So we're going to hit it hard. All right, that is actually it, okay? So that's Brightspace, that's the syllabus, that's who I am. That's what we're doing in this class. I'm going to tell you something. This class is awesome, and I look forward to working with you. Good luck.